Video part 3 of Aice Motion Review. Question 1. A radio-controlled toy car travels along a straight line for a time of 15 seconds. The variation with time t of the velocity v of the car is shown below. So here is a graph that shows how the velocity change over time for this toy car. What is the average velocity of the toy car for the journey shown by the graph? This is the Aice Physics foldable. The first page, we have all the definitions, and let me look for average velocity. Average velocity is equal to the total displacement over total time. On part 2 video, we discuss that when a graph velocity time is given, the area under the line can determine the value of distance and displacement. There are two different approaches for distance and displacement, but in this case, we are looking for the displacement. So that way, we can calculate the average velocity. So in a written form, the average velocity is equal to the total displacement over total time. We do have the total time from 0 to 15 seconds, but you need to determine the displacement. In this yellow shaded area is the velocity of this toy car, constant for 3 meters per second up to during 10 seconds. Now this blue shade section indicates a sudden change in the speed of this toy car from 3 meters per second to 6 meters per second and going in an opposite direction, because here indicates a negative. And this happened in an interval of 5 seconds, from 10 to 15 seconds. To calculate the distance or displacement, we need to look the area under the line for each section. Here we have a rectangle, and here you have another rectangle. So in this yellow shade, the area of this rectangle is this side, which is 10, times this side, which is 3. So the area corresponds to 30 meters. For this one, the blue shade, the area is this length, which is 5, times this length, which is 6. So here we have 30 meters. But here in this blue shade, this value is negative. So that area here is a negative number. So for displacement, we do consider the sign that we obtain when we calculate the area of the geometric shape formed by the line. This is very interesting. So the total displacement here, because this is positive and this is negative, the total displacement is 0. So the average velocity will be 0 over this time, which is 0. So that's the answer. Question 2. A stone is dropped from a height of 20 meters above the water. So this diagram kind of helps to understand the story. So here is a stone that is going to be dropped, is 20 meters above the water, hits the water, and then is saying that the graph shows a variation with time of the velocity of the stone. And here is showing, I'm going to go back in a minute, but I want to read the question. Which statement describes the approximate position of the stone 4 seconds after it's dropped? Now let me interpret this graph. So this graph indicates the whole story. So here the stone is dropped with initial velocity 0. It's accelerating at constant acceleration which means that is increasing speed at constant rate. And this rate here is the acceleration of gravity, which is 9.81 meters per second square. And when reaches the water, so here is when reaches the water, all right, and reaches the water at 20 meters per second. So right here, reaches the water at 20 meters per second. That's the speed. The speed goes from 0 to 20 meters per second. And suddenly, quickly change its speed from 20 to 5. So here you see there is a gap here, just to indicate that in 2+ microseconds, this shift happened. And then it's going to keep falling in the water now during from 2 seconds to 4 seconds at constant speed of 5 meters per second. So 5 meters per second, constant speed right here. So let me read the first statement to see if it's correct. Is a distance of 10 meters above the surface of water. The time that it stays above the water is right here, 2 seconds. So the area of this triangle is going to determine the distance. So let's see what happened. So here is a right triangle. So we can calculate the area is base, which is 2, times height, which is 20, divided by 2. So the area here is 20 meters. So this is not correct. This is false. Option B, it's a distance of 10 meters below the surface of the water. Below the surface of water, you'll be from 2 to 4 seconds. So that will be the area right here of this rectangle. So the area here is base, which is 4 minus 2, 2 times height, which is 5. So this is 10 meters. Yes. So is the position of the stone 4 seconds after it's dropped is a distance 10 meters below the surface of water. So that's correct. Which makes the option C that said a distance of 20 meters below the surface of water, this is false. This is 10 meters, not 20. So the rest is what we call fillers. I mean, wrong options, just to have 4 options. So the correct is B. Question 3. A particle has velocity v and angle theta to the horizontal. The components of the particle's velocity are vv upwards in the vertical direction and vh to the right in the horizontal direction as shown. What are expressions for the magnitude of v and for the angle theta? This question is super easy. All that we need to do is move this vector vv right here. So every time that we have a initial velocity that make an angle with the horizontal, that's the approach. This is our vv. To find the magnitude of v, because this is a right triangle, we use Pythagorean theorem, which is v squared is vv squared plus vh squared. For the magnitude is the square root of vv squared plus vh squared. So you have option A and option B with these results. So let's check the angle. So the tangent of this angle is the opposite, which is VV, over adjacent, which is VH. So this angle is the inverse of a tangent of VV over VH. Pretty much what we need to find is the order here. So this is this one, VV over VH. So this is option B. Question number 4. The graph shows the variation of velocity V with time t for an object. So here is the graph. The object passes a fixed point at time t equals 0. T equals 0. What is the displacement of the object from the fixed point at times t equal 5 seconds, and what is the acceleration of the object? So from the fixed point times 0 to 5, what we have here? We have a geometric shape that we talked about before. So this is a trapezoid. Yes. So in a velocity time graph, the area under this line corresponds to the distance or displacement. In this case, it's asking the displacement, which is fine. We are not going to be adding partial areas. So that's the only area that we can calculate here. So the area of this trapezoid is the big base plus a smaller base times height over 2. Okay, so now we have. So this area corresponds to the displacement. The big base here is 24. The smaller base here is 4. The height is 5 divided by 2. If you have a hard time to find these values, you just need to flip and place the trapezoid in front of you so you can see better. The longer base, the smaller base, and the height. So the result of this is 70 meters. Great. So now we know the value of the displacement. To find the acceleration, we can also use this graph to collect the information. So acceleration by definition is the change in velocity over time. The correct way to say is acceleration is the rate of change in velocity. There we go. So this means here is the final velocity minus initial velocity, final time minus initial time. So what do we have here based on this graph? Final velocity is 24, initial velocity is 4, final time is 5, and initial is 0. So now we have 20 divided by 5, which is 4 meters per second square. So now we need to find those two numbers in one of the options. So this displacement is 70. I have these and I have these. Acceleration is 4. I have just this one. So that's the right answer. Question number 5. A ball is released from rest, okay, initial velocity 0, above a horizontal surface. It strikes the surface and bounces several times. The velocity time graph for the first 2 bounces is shown. So how do I identify the bouncing here? So I'm gonna give you a hint. Every time that you see this vertical line, that's the bounce. So first bounce, second bounce. If you kept going, and then you count again, third bounce, fourth bounce, and so forth. So this is an indication right here, is the first bounce. And this is the second bounce. And looks like stop right there. So the question is asking the maximum height of the ball after the first bounce. So let me do a diagram that go with this graph. So is release from rest right here. and hits the ground at 3 meters per second. Right here, 3 meters per second. So here I'm going to describe each point of this graph to try to make sense. So here at 1, right here, 1, right? Ball is dropped with VI 0, initial velocity 0. On step 2, the ball hits the surface with 3 meters per second. Then at 3, the ball is going to change direction. So between 2, 3, and 4 happen very quickly. There is even no time interval here. Like instantly, the ball hits the ground and bounce back with a velocity that is less than the one that hit the ground. Maybe because the loss of kinetic energy into other types of energy like sound, heat. So the ball here is going to bounce back with a different value, and the negative indicates that it's going to bounce back upward with a speed of 2 meters per second. Then at 5, the ball stops in the air. And then at 6, the ball hits the ground with a velocity of 2 meters per second. And at 7 happened the same as 3. The shift with velocity. So right here, it didn't finish. It's it stopped right here. But we know there is a first bounce and second bounce right here in this area. So now it's asking what is the maximal height for the ball after the first bounce. So we are looking right here, first bounce. So the only section that we can actually calculate a distance or height is this triangle right here. So now we have this triangle is going to help us to determine the height of the ball after its first bounce. So because it's the area of a right triangle, so that's the formula. The base here will be 0.5 minus 0.3, which is 0.2. The height is minus 2 and divided by 2. So the area of this shaded triangle is negative 0.2 meter. If the problem was asking displacement, this is something that you want to consider, but it's not say nothing, so you just say the maximum height. In terms of magnitude, you'll be just 0.2 meter, which is option A. Next question. The graph shows how the velocity of a ball varies with time. For the moment, it's hit vertically upwards from the ground. So this is the graph. I'm going back to the graph in a minute. Let me read the question. What is the displacement of the ball from the ground after time of 3 seconds? Okay, so that's the difference between distance and displacement. If the problem was asking what is the distance of the ball from the ground after a time of 3 seconds, then you calculate this area plus this area and you add them independently of one will be negative and the other one positive or vice versa. But because it's asking displacement, we need to take in consideration the sign of each area that we are going to calculate here. Now, in this case, the ball is being thrown upward, vertically upward from the ground. And what happened is, when it reaches the maximum height, the velocity here is 0, okay? So this is VF here going up is 0. This is VI. Okay, VI here is a 20 meters per second. And the graph also indicates, let me cut right here, indicates a decrease of velocity. So that makes sense because as going up, the velocity is going from a value of 20 meters per second, ended up with 0. So is decelerating. Is decelerating, so the velocity is decreasing. Makes sense. Reaches the maximum height and stops. So final velocity here is 0. And then changes direction and starts to fall back down. And doesn't show the rest of the story. It says that up to 1 second. So 1 second is from the top to up to reach a velocity of 10 meters per second. And going up is taking 2 seconds going up. Coming down up to what the graph allows us to see is 1 second. Then I have here two graphs under this line. I have this triangle and I have this triangle. Now, because it says that the area under the graph line, so this is not under, this is above, right? But that's okay. It's just like a term that goes with the way that we do graphing. So the area under the line. So you can get this, but because this is negative, so the area is going to be above the line. Be careful because you cannot consider this trapezoid here that is formed in this area, because from 0 to 2 seconds, that is not the section of the story. The story is on the other side. So up to 2 seconds reaches the highest altitude, highest displacement, and from here to here it starts to fall back down. So it's after 2 seconds. So it's wrong to consider the area for this line area of a trapezoid, because this is not part of the problem. The problem is say after 2 seconds up to 3 seconds, this is what's happening. So that's why this is the area that we need to be looking at. So the area of the yellow shade triangle is 20 meters, and the area of the blue shade triangle is negative 5 meters. So in terms of displacement, we are going to consider the sign of those areas. If it was distance, no. Distance will be 25 meters. But displacement will be 20 meters minus 5 meters, which is equal to 15 meters. And option A is the answer. Now, if you want to answer this question using motion equations, you can. So let's set up the table for when the ball is going up. So the initial velocity is 20, the final velocity is 0, distance, that's what we want to know, right? Acceleration is decelerating, so it's minus 9.8, and the time here is 2 seconds. So now we can calculate this distance using the second equation, and the result is 20.4 meters. Now remember, the acceleration here is negative because it's decelerating. Now what happens when the ball is coming down up to 3 seconds? So that's the initial velocity is 0, final velocity we don't know. Actually we do here, which is minus 10. D is what we are looking for. Acceleration is accelerating now, is 9.8 meters per second square, and time here is 1 second. So to simplify this, I'm just using straightforward the second equation with the simplified formula since VI is 0. So that will be 4.9 times time square is 4.9, right? So now what I'm going to do is I'm going to add both distances, which is 20.4 minus 4.9 is 15.5. It's a little bit different of the one that we obtained graphically, but the options here closest to this value be also 15 meters. So there are two ways to answer this question. You pick the one that is easier for you to understand. Question number 7. The velocity of electric cars changes as shown, right? What is the acceleration of the car? Well, easy. We just need to observe here. The acceleration will be the change in velocity over time. So here we have, let me look closer, the initial velocity is 0. The final velocity here is 10. It looks like each one is, okay, so I need to know how much is each box. So I have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 boxes. That corresponds of a change of 50. And the unit here is kilometer per hour. So 50 kilometers per hour, which is the difference between 150 and 100. I have between them 10 boxes. So this corresponds to 10 boxes, which means that one box will be 50 kilometers per hour over 10. So each box corresponds to 5 kilometers per hour. Now I can read this value. So this is just one little tiny box. So whatever I read here, I have to add 5. So that is 105 kilometers per hour. Okay, by definition, acceleration is the change in velocity over change in time. So my change in velocity, my final here is 105 kilometers per hour minus the initial one, which is 0, and the time is 4 seconds minus and 0. Okay, so I got the extremes. So 105 minus 0, and this is 4 minus 0. Okay, we have a problem here. The unit here is kilometers per hour, and my answer is in meters per second. So we need to convert 105 kilometers per hour to meters per second. So let's start. First thing you write in terms of a fraction here, because this dash means a fraction. So 105 kilometers per hour. And now we have to convert one by one. I'm going to start with kilometers to meter and put hours on a hold. And these you multiply, okay, multiply by, and then you repeat right here your kilometer. So 1 kilometer has how many meters? So is 1,000 meters. So I stop right there. Great. I'm going to convert these very easily. I just cancel out, and I have my result in meter. So what I do with hour? So hour needs to go on the top. Hour. 1 hour in terms of seconds is 3,600 seconds. Okay? So let's see how I do with this. So now I'm going to cancel kilometer with kilometer, hour with hour. What is left? Meter and second. Perfect. So now I get my calculator, and 105 times 1,000 is equal, divided by 3,600 is this number, 29.16 meters per second. Okay, so now my A is 29 meters per second, 29.16 meters per second over 4 seconds. So my acceleration is, now I get this number and divide by 4 and 7.29. 7.29 meters per second square. Because see, this S with this S is going to multiply, so that's how I get E squared. So which one is the very close? Okay, I'll take this 7.3, close enough. Another story here. Question 8. A hot air balloon is moving vertically upwards with a constant speed of 3 meters per second. A sandbag is dropped from the balloon. It takes 5 seconds for the sandbag to fall to the ground. What was the height of the balloon when the sandbag was released? Here is the diagram that represents this story. So the balloon is moving vertically with a speed of 3 meters per second upward, and the sand is being dropped here, right? Now remember one thing. This sandbag was not dropped from rest, was dropped from something that was in motion, and was in motion in the opposite direction at which is going to be dropped. So the initial velocity for this sandbag is 3 meters per second, but negative because it's going with the opposite direction of the original motion that was going. So the final velocity, I don't know, is the velocity that hit the ground. The distance is what I'm looking for. The acceleration now is going to accelerate at 9.8 meters per second square, and the time is in 5 seconds because that the story says that that's the time that takes for the sandbag hits the ground. So, and then I'm going to use my equation number 2 because I'm looking for distance. I do have initial velocity and I have time. So here is the substitution, and my distance is 107.5. The option closer to this value is option B. And remember, in this problem, if something like that happen in your test, remember the initial velocity is not 0. Question number 9. A car at rest in a traffic highway moves forward in a straight line and then comes to rest again. The graph shows the variation with time of its displacement. What is the speed while it's moving? So here in this graph, displacement, time, we have a 3 section. Let me try to color. This is one section, and this is another section. And let's make this like this. Okay, we have 3 sections. Section A, Section B, and Section C. So let's thinking about the displacement time, okay? What happened at Section A? What happened at Section B? And what is happening at Section C? So the first question you need to ask is, the object is moving at Section A? Well, as the time goes by, the car is at 30 meters away from the reference point without moving. The distance is the same. So an A object is not moving. Then what happened here? Well, after 50 seconds, so then the car starts to move, right? But how? With a constant velocity. This line means constant velocity. So B is moving at constant velocity. How do I know? Because we can see here equal increments with time. So which means that this car is not accelerating, is not decelerating, It just stay there with the same speed moving. And then what happened at C? The same thing that happened at A. A flat line here means now this car from 100 seconds up to 140 seconds is not moving. So the car is not moving. So the question is asking the speed while is moving. So now we are going to calculate the speed is the change in distance or displacement in this case over time. Okay? So speed is change in displacement. So here we have the final is 70 and the initial is 30. 70 minus 30. Change means the final minus initial all the time. And what is the corresponding time? This is 100 and this is 50, right? This is 50. So 100 minus 50, yeah. So speed here is, this will be 40 and this will be 50. So the speed is 0.8 meters per second. And we have an answer, which is B. So this will be my last question from this video before getting too long. So number 10, a car travels along a straight horizontal road. The graph shows the variation of the velocity of the car with time for 6 seconds of its journey. The brakes of the car are applied from t is equal 1 to 4. How far does the car travel while the brakes are applied? Okay, so I need to know what happened between 1 second to 4 seconds. So that is what I need to look at. So it's asking how far. So the distance on a velocity time graph can be determined with the area under the line. So I have this area, this is the line, and this is the complete area right here, which is a trapezoid. So the area of this trapezoid is the big base, which is, okay, now I need to figure out how much is each box. So I have 30, and here is 20, the difference is 10, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So each box corresponds to 1 meters per second. So this is 22 meters per second. So let me get it smaller here. Plus, and the difference between 4 and 1. Okay, that's the height, but I'm looking for this one. Okay, so let me look here. The correspondent of this is the smaller base. So each box is 1. So here should be 8. 8, 9, 10, yes, 8. Plus 8 times the height here is, I'm following the formula, is big base plus small base times height over 2. And the height here is 4 minus 1, which is 3 over 2. So I just translated everything here into this numerical value. So A is 45 meters. So this is option B. Easy problem.